So I will continue with the discussion which I was having in last session. In this session, I will be showing you the complete model which we started last time. As Dr. Mohammad Raza mentioned, that it is a reinforced concrete 10-story building with reinforced concrete frame and reinforced concrete shear walls. And I explained in last lecture about this particular workflow which we can have while working in SAP 2000 and ETABS. So we started the model already, and then we defined materials and then defined the cross-section properties. And while defining the cross-section properties, we actually imported the materials in that actually each of the cross-section needs to be associated with a particular material. After defining cross sections, we draw the elements, actually define the elements. And while defining the elements, we know that we have to select a particular cross section. So each element is associated with a cross section, which is again associated with a material. After drawing the materials, we can start the process of defining the load vector or defining the loads. And for that, the first step is to define a load pattern, and then that pattern can be used to apply different point loads, line loads, or area loads, for example. So each of those point load or area load or any uniformly distributed load, for example, should be applied within a particular load pattern. So when you apply them to a particular node or element, you have to associate that loading uh, with a particular load pattern. Then that load pattern is then called in a load case. So we will be defining load cases, and within those load cases we will be importing the load patterns. The analysis will be performed for load cases, and then the program have an additional capability to combine the results of individual load cases into what we call as load combinations. So we can define also the load combinations, but they will be used for the purpose of structural design. So different load cases can be designed, can be combined to get the envelope results for design purpose. So this load combination option obviously is only required if you want the automated design by the program. But if you just want to see the response of the structure for a particular load, you can define the load cases and then run the analysis. After that, you have to assign the joint restraints, the support conditions in order to complete the modeling part. And if the analysis is supposed to be dynamic analysis, for that you need to tell the program how it should develop the mass matrix of the structure, because it is an integral part of the governing equation of dynamic equation of motion. So the mass source need to be defined, and then we can run the analysis and then we can display different results. So we have already defined the load patterns, and let me just quickly show you about load cases, and then I have already run the analysis, so I can show you some of the results which you can see after running the analysis. Especially I'll be focusing on the equivalent lateral force procedure, for which I have already defined the automated lateral loads according to ASCE 716. So I have selected this particular code, and obviously you will be providing the different inputs required by that code to determine the equivalent static forces. For example, the short period and long period spectral acceleration values, and the site class, and also the long period transition period, for example TL. And all of those inputs will be determined, will be used to calculate the equivalent lateral forces by program. So you don't need to apply individually to each of the floor diaphragm these forces. Once you define a load pattern for this case, this particular code, and then you import that load pattern into a particular load case, then the program will automatically apply those forces to each floor, and then you can run the analysis. So unlike the other gravity loads and superimposed dead loads and live loads which you apply manually and then import them into a particular load case, here you just need to define a pattern and then use that pattern to define a load case. So I'll be just opening the same model. Let's assume that the geometry is completed already, and let me go to the base of that model in XY view, and let me go down This is the floor plan I am seeing because of this cyan color I can see. So I can go down and go to the base of this particular model to select all the nodes and assign them as fixed supports, for example. Right. So this is the base plan level, and then I can select all the nodes. Let's assume that I want to assign them a fixed support condition. So I can just select all the nodes, and you can see here 44 points selected at the bottom, and there I can go to assign and then joint. Obviously this model is locked because I have already run the analysis, so I cannot change anything. But if there was if it was not locked, let me just quickly open the other model which is not run already without analysis. So I'll go back again in the XY view and then go down by using this arrow. So this is the base. I can select all those points, 44 points selected, go to assign, joint, and then restraints. And here I can select, for example, all 6 degrees of freedom should be restrained for these particular 44 points. I can also select if I want an other support condition. For example, the nodes associated with the base of shear walls are sometimes assigned with a hinge support and not the fixed support. So I can do that also. So by clicking apply and clicking OK, I have assigned all the fixed supports to my model. So continuing with the definition of load cases, we have already defined a load pattern, which was the first step. You can see here that two equivalent lateral force load patterns are already defined in last session, and we have selected ASC 716 for the auto lateral load calculation. I can modify that, and you can see here that these were the inputs which should ideally be for your particular site, correspond to your particular structure and all that. So assuming that these are the values, I can just define those patterns in both X and Y directions. This is for Y direction, global Y direction. The previous one was for X direction. And then I can go to define and load cases. The second step in defining the loads actually. And here I will define different load cases and import or call those patterns within them. So for example, you can see that I have defined an ELF X load case. I can modify it to show you. I have set its type as the static analysis, and there are other analysis types also. I think you will be familiar with response spectrum and time history analysis in the context of seismic analysis procedures. This obviously will be a linear static analysis, so therefore it will start with the zero initial conditions, no prior loading or no stiffness degradation prior to the analysis. So it will be using the initial stiffness for the purpose of this analysis. In this particular load case, I have added one load pattern which is ELFX, which I just defined in the last step. And if I want to apply any code specified factors to my structure forces, I can use the scale factor option to modify this, add a scale factor, and then modify it will be changed here. So it will be a linear analysis. So I click OK. Obviously this option is telling you that the program will be calculating the seismic weight based on this particular mass source. So let me just quickly show you the default mass source which the program is using. So it will be in define and mass source. Yeah, here you can see that this is the default mass source which the program is using. And if I want if we want, I can modify that one also. So currently you can see here that it contains only the element self mass, and if there is any additional mass assigned which is not assigned currently in our model, but if there is, it will be included to calculate the mass of the structure, which will be converted to the seismic weight. But if I want to add, for example, some percentage of live load, I can add it here. I can select the pattern, for example, have to define a pattern for live load, and then using, let's say, this multiplier, let's say 25% of the live load can be added, and then it will be added to this same mass source. Currently with no live load option available or applied, we can just go with this for the purpose of this demonstration. So then I go to again to the define load cases and then show you, for example, the ELFY load case. I can modify it and show you what it looks like. The only difference is that this time I selected the ELFY load pattern to be applied in this particular load case. Other things will be same. So let's say that I have already defined these two load cases. So I am ready to run the analysis for these two load cases. I have also defined the response spectrum load case in X and Y direction separately, and the time history analysis for X and Y direction separately. So you can check them also after this particular session. But here I'll be just explaining the results obtained from the equivalent lateral force procedure. Uh, so let me just open the model which is already run. Okay, even before doing that, let me show you the analysis options which you will be checking before running the analysis. So, okay, let me just open the same old model. And then after, let's say you define the loads and boundary conditions and all the modeling is done and you are ready to run the analysis, you will go in that analysis menu. And first thing you can check is set analysis options. Uh, Here you can tell the program that the analysis should be run for which degrees of freedom. For example, if you are running the analysis for a two-dimensional plane, two-directional plane frame, you can check this option and it will uncheck the degrees of freedom which are not applicable for this particular two-dimensional analysis. For example, if your frame is in XZ plane, then there is no y direction for which the analysis should be performed. So it unchecked the translational degree of freedom in y direction and the rotational degrees of freedom in the y directions, rx and rz. So the analysis will only be performed in 3 degrees of freedom, which is 2 translations in that particular xz plane and 1 rotation in that particular xz plane, which will be the rotation about y axis. Similarly, but this particular example is a three-dimensional model, so I will be just selecting the space frame, which means all 6 degrees of freedom should be included in the analysis. Similarly, some of the other options which you can check, but this is the important thing which you should mention or check before running the analysis. And then another thing you can check is set load cases to run. Here the program will list down all the load cases which you have defined, but for a particular run of the analysis you may not want all of them to run at the same time. Currently all of their status is not run and the action which is to be taken by the program is run. So if I want, I can just select a particular analysis to run only when I click on run now. So I can just set them all of them to, for example, do not run, and then I can just particularly select 2 of them and change their status to run. So when I click now run now here, or if I go to this, click on this play button on top or run analysis button available in that analyze menu, you will see that only these 2 cases will be running the analysis. So after this you can just click on this run now and it will start running the analysis. It may take a few minutes to complete the analysis depending upon the level of complexity of the model and also the type of applied loading, whether it is static or dynamic. So let me just open the model which is already run for these cases. This is the model which is run already. So you can see here that now it is logged after completing the analysis, so which means the all the options available in display menu are available now. Previously they were not available because the analysis was not complete. If I click on this log button again, the model will be unlocked and all the analysis results will be just disappear and we have to run the analysis again. So first thing you can see is the after running the analysis, you can select a particular view, for example, for which you want to display the results. Let's say this is the three-dimensional view which I have selected. Click on that area and then go to display, and let's say I want to show the deformed shape of the structure under a particular load case which I have defined. So if I click on that, I can see this this form. I can also open it from this particular button, show deformed shape. The same option will appear. And here you can see that I can select a particular load case or a particular combination which I have defined. In this particular model, I haven't defined any combinations. And by the way, you can also define the combinations after running the analysis, because the program just have to combine the same analysis cases results in order to produce the results of load combination. So it doesn't apply the combination and run the analysis for combination. It simply uses the results from different cases to combine them. So the first thing I will check is, let's say, the mode shapes. So I will be selecting the modal case, which is the default case. You cannot modify, you cannot actually delete that case. It will always be there as the first case for running the analysis. And I can select the mode number, let's say mode number 1, and some of the viewing options, scaling options, you can explore yourself. And then I can simply click on apply, and here I can simply animate it. It will show me the time period of first mode, the frequency of the first mode on top, and I can start its animation. And you can see here that the first mode is actually the translational fundamental sway mode in X direction of the building. Similarly, I can also select, let's say, mode number 2 here in the model, and then again can see, and then again start animation. So you can see here that it is the fundamental translational mode in the Y direction of the structure. And similarly, the third mode will be, I think, the torsional mode, the first torsional mode. So you can see here that it has a time period of 1.32 seconds, and it is the first torsional mode. Similarly, the fourth mode may be the second mode in X direction. So let me just visualize the fourth mode. Yes, it is the second mode shape in the X direction of the building. So again, you can see. And fifth would be maybe the second mode in Y direction. Yes, it is the second mode in Y direction. So it is always fun to play with some of the animations for first few vibration modes, and you can also see their natural time periods and corresponding frequencies on top here. You can also see the data associated with the determination of mode shapes and modal participation factors and all other modal properties by clicking on display and then show tables, this option. And here actually all the analysis results can be shown or displayed in the form of tables. So whatever result you can visualize using other options in the display menu, you can get their actual numbers from this display show tables option. So all the model definition is defined here in the form of tables, and all the analysis results are defined here in this particular table. You can see here that a total of 27 tables are generated, which include all the joint information, element outputs, and structure output. The particular modal information is available in the structure output and then modal information. And then these are the 5 tables generated by the program. And you can, for example, see this particular modal participating mass ratios and click OK, and it will populate a table for those number of vibration modes which were defined by default in the modal case. So there were total 12 number of vibration modes defined in the modal case by default. So it reports its time periods and the modal participating mass ratios in the 3 translational degrees of freedom and then 3 rotational degrees of freedom on this side. And then it is also reporting the cumulative modal mass. For example, you can see here that the first mode here is having a 79% participation in X direction, which means it is the first mode in X direction. Then the second highest participation is in the fourth mode. So this is the second mode in X direction. Then the third highest is in the seventh mode. So seventh mode is the third mode in X direction. Similarly, Y modes are, this is having the highest participation in Y. So second mode is the first mode in y direction. Similarly, the fifth mode according to software numbering is the second mode in y direction, and also you can see you can arrange them and see that what is the third mode in y direction. If you look at the cumulative numbers, the 90% mass participation is just fulfilled within the first two modes. So the third mode, when you include somewhere here, the participation increased from 90%, which is around 94% for next direction. For y direction, actually we need to have more number of modes in order to complete a 90% participation, because the cumulative mass participation is still 86% up till the 12 number of modes. If we want, we can run the analysis again by changing the number of vibration modes. Here you can go to define again, load cases, and this is the default modal case which is already there. You can modify it and change the number of vibration modes which the program needs to be calculated. So instead of 12, we can select, let's say, 20 or 30 vibration modes, and program will be able to calculate that. So after modal analysis results, we can go again to display, and let's say I go to maybe going to the forces. So show forces, and again forces can be for either joints, frames or shells. So I can go, let's say, for frames, and here again I have to select the particular case. Let's say I select the ELFX case, and then let's say I have to select the M33, which is the primary bending moment in beams, the moment about 3 local axis, and this is the force type, and then I can just apply, and I can see the bending moment in all the frame elements. Similarly, if I want axial force in all the frame elements, let's say columns, I can just select that one, and I can select the envelope or step, but this option is mostly available for multi-step analysis. ELF is just a direct linear static analysis, and therefore I can, that option is not available. Similarly, I can also go for shear 2. This is the shear force in frame elements. I can change the you can say the colors of different visualizations. In order for convenient visualization, I can change it from options, colors, and then display. And here you can see all the display options and different colors, and you can play with them to actually visualize the results more clearly. Similarly, I can show the deformed shape, for example, for ELF cases. Again the same thing, but instead of modal, I'll be selecting ELFX, and the scaling can be either automatic or user defined. Let me first try automatic. Yes, I think you can see here that since the forces in ELFX particular case were the story forces in X direction, I can start its animation and see that the building is primarily swaying in X direction. Similarly, for ELFY, you can expect that it will primarily have a sway deflection in Y direction. So here you can see that it has the sway direction in Y direction. Some other results we can see here in display, and then maybe going to for example, show plot functions. Here we can select different variables to plot ourselves. For example, let's see, okay, this option is only available for multi-stepped cases, for example the linear time history analysis, because they can be plotted as a function of either time or input energy. For this particular demonstration, we will just skip the response spectrum and time history analysis and just focus on the ELF results. Then I'll click on this again, display and show tables, and maybe this time we can go for element output. And also you can see, for example, in structure output, all the base reactions for each particular load case will be reported in this particular table. So let me just this option uncheck the modal information, and let's say I can go for frame output and then element forces. So these two tables the program will be actually generating for me now. So it will be just populating. For example, the first table is base reactions. For all the cases, it is reporting me the base reaction, but actually I have to select a particular load case also there. So let me just again go to the same display option, show tables, and I have to select the load pattern, load cases also. So currently the dead and modal were selected. Let me select, let's say, ELFX and click OK, and then click OK. So for ELFX, it calculated me the base reactions. You can see here that the global FX, this should be actually the base shear calculated by the program using ASE 716, because this is the base horizontal reaction for this particular load case ELFX. You can see here that the other two numbers, the y direction reaction and z direction reaction, they are negligible actually because of numerical issues. They are being shown here, but actually they will be zero because program won't be calculating in y direction and z direction because no force was applied in those directions. Similarly, the base moment about x and z will be here. You can see that for base moment about the primary force, if it is applied in x direction, the moment will be mainly generated about y direction, the base moment. So this should be the number. Let me just copy that maybe and show it more clearly in Excel. So maybe export current table to Excel, and it should show me these numbers in Excel. Yeah, so an Excel sheet is opened, and here you can see this is actually the primary base bending moment which the program has calculated, and the equivalent lateral forces have produced this primary bending moment. Uh, Obviously, currently we are using some random numbers as an input, so these results won't make sense actually. Uh, but you can get all of your results and export it to Excel like that. Any table can be exported like this. Element forces also you can see, and this it will create a whole detailed table which you can sort also. It You can see here that these are around more than 7,000 entries. All these 6 element forces, the axial force, and then two shear forces about two cross-sectional axes V2 and V3, torsion, and two moments, moment about 2 and 3 axes. All of them are reported here. So if for example I can sort them using the ELF case, I can just select them, ELF case, and you can see here that for frame text 1, it have generated for me 5 different uh, rows, and they are actually the values of all 6 element forces at 5 locations along the length of that frame. They are called stations. So starting from 0, 500, 1000, 1500, and 2000. So this particular element was having a length of 2000 millimeters, and it reported the results for ELF case, which was a linear static case, all 6 results element forces for 5 different locations along the length of this particular element. So I have to sort this table obviously because it is having a very detailed data, but any element can also be clicked after the analysis to show its individual results. For example, I can click on a particular element, it will be selected, but if I click if I have a right click on it, sorry, I must first open the particular view in which the results are available. So let's just plot the axial force diagram, shear force diagram V2 for the ELF load case. Okay, it is plotted, and now let me select a particular column, let's say this particular column. Let me just zoom up it a bit and select a particular column, maybe this one. Yeah, if I right click on a particular column, I will see all of its details for this particular element. It can be a column or a beam or a other element also. So I have to select the case and then which results I want to see. Maybe V2 and M3, which is the major shear and major bending moment. So it shows me the equivalent loads. It show me the V2 shear diagram, M3 moment diagram. It can also show some of the other numbers. You can scroll this and have peak values and all that. So please explore all these analysis results yourself, and you will be seeing that it is some real fun to express and show the and report the results and plot them yourself and have a decision making based on those results.